Yeah, 12. This is the long-awaited final video in the energy and enthalpy kind of unit, and it's about bond enthalpies. I'm trying out a new style of video today. I'm going to be trying to write along with it using my magic pen, and so please bear with me if it's a little bit less smooth than my usual Radio 4 tones. Okay, so these are the specification points for bond enthalpies. There's not very many. It's mostly what we're learning today is how to apply it. I have a very specific method that I would like you to use. So what is a bond enthalpy? The bond enthalpy we can think of as the energy that is held inside a bond. We know that breaking bonds requires energy because a bond is obviously something that's keeping two things together. It's quite obvious you're going to use energy to break those apart. The flip side of that people don't really think of is that making bonds therefore releases energy. Sometimes a little bit strange to think of, other than the fact that no energy can be created or destroyed. So if we're putting energy into break a bond, we have to be releasing energy when we make a bond. It has to be in a lower place in energy. So we can think of this in terms of a sort of energy profile diagram, whereby we have this sort of step. It's going to be breaking bonds. That's requiring energy. I'm going from two things that are bonded together, like maybe a carbon and a hydrogen here. When I separate them, I've had to put in some energy to have these two things as separate radicals. Therefore, if I were to form a bond again, I would release the same amount of energy that I had to put in to break them. Okay, so using that knowledge, we need to know what the average bond dissociation enthalpy is, and that's the energy to break 1 mole of the same bond across a range of gaseous compounds and separating the resulting particles to infinity. Let's go through this. The energy required to break 1 mole of the same bond across a range, 1 mole of the same bond, that's fair enough. So that might be 1 mole of CH bonds across a range of compounds. That is because you could have CH4, that's got CH bonds in it. You could have C2H6, that's got CH bonds in it. You could have CH3Cl, that's got CH bonds in it. And all of those bonds are going to have a slightly different dissociation enthalpy, or bond enthalpy. So that we average them out, we average over a range of compounds. And we separate the resulting particles to infinity. Obviously, that is impossible, but we separate them to a sufficiently large distance that they do not have any effect on each other anymore. You can't, so they're not attracting each other. The word dissociation enthalpy, we use the word dissociation sometimes instead of bond enthalpy. It means the same thing, dissociation, as in to split apart, to dissociate, so that the two atoms are no longer associated with each other. You might think average over what? As I said, there's a lot of different chemicals with, for example, C double bond C in. I mean, this could be connected to H's. As you can see, I'm really good at drawing on here. It could be connected to other carbons. And as I said, these are all going to carry different bond enthalpies. But here we've got some typical bond enthalpies. Now, you'll notice they've not put a sign on these. That's because we know if we're making a bond, it's going to be negative, and if we're breaking a bond, it's going to be positive. It's just the general sort of energy inside that bond. So for a carbon-carbon double bond, it's about 619. For a carbon single bond, it's about 347, so just under half, sorry. And don't be too surprised if when you see an exam, you see different bond enthalpies each time slightly, because as I said, it's an average over a range of compounds, and there can be different averages. So how can we use this? Well, the enthalpy of reaction, so our delta HR, is equal to the sum of the bond enthalpies of the reactants, which we can write like this, minus the sum of the bond enthalpies of the products. Because obviously, in a reaction, if I've got some reactants that have this much energy in their bonds, and I change them to some products that have this much energy in their bonds, then the difference between their bond energies is going to be delta HR. Okay, that's all that's happened when we've changed from our reactants to our products. We've just changed the bonds. So if we find out what the difference between the bond energies is, we work out the difference. We work out the enthalpy change during the reaction. So let's try a question. This is from a genuine past paper. Readjust myself slightly so that I'm going to be able to write better. And I'm going to show you exactly how I'd like you to write these sort of like questions out. So we've got a reaction. Chloroethene is being made from dichloroethane. And we've got this reaction that it says up here. We've got chloroethene over here, chloroethane, and hydrochloric acid. And we've got a table with some bond enthalpies. Okay? We've got to work out delta HR. Now we know that delta HR is the sum of the reactants minus the sum of the products. This symbol here is a capital sigma. Well, it's meant to be a capital sigma, by the way, for those people who don't do maths at A level. It just means sum of. It means adding them all up. It will become quite obvious what we're doing with those in a second. So the first thing I would always do is write out the equation. I know it already says it up there, and you're going to be able to see it a lot less well in my version. Now, I would write, made a bit of a mistake here, because I don't think it's actually that useful to see it as, to see the chemicals as the formula. I think it's much better when you're doing these calculations to draw out the structures showing all of the bonds. So I've got this is chloroethene. Oops, it's not a double bond. Silly me, I made a mistake there. So it's actually dichloroethane. I thought it was dichloroethene. Oops. Rub that out. As I said, these videos will get smoother as I get better at using this piece of apparatus. So we've got dichloroethane, which will show all of the bonds. Doesn't matter where you draw each bond, but you need to show them all. Then you've got to draw an arrow. And on the other side, you show all the bonds. So now we've got a double bond. H, Cl, Cl, and an HCl. Okay, ready to start doing the question now. The next thing I would do, I'm going to pull this down here to help me out, so I can see it. The next thing I would do is draw a line down the middle of the arrow right here. And then what we're going to do is going to write down how many of each bond we've got and what the total enthalpy from that is. So we've got we have 1, 2, 3, 4 CH bonds. So we've got 4 times CH, which equals 4 times 413. We have 1, 2 CCl bonds. So 2 times CCl, which is 2 times 3, 4, 6. And we have 1 times C bond, which is just going to be 3, 4, 7. To find the total bond enthalpy on this side, we then have to add the sum of all these up, don't we? So we'll do 4 times 413. I have to reach for my calculator. Plus 2 times 346 plus 347, which I make to be 2,691. I've written a lovely purple. Okay, same thing on this side. Let's count the CH bonds. 1, 2, and I've drawn this wrong. It should be a CH bond. Apologies. All over the place. This pen is distracting me heavily. And now I've drawn it correctly. 3. Well done to anybody who'd spotted that mistake before I pointed it out myself. Okay, so we've got 3 times CH bonds. So that's 3 times 413 this time. We've got 1 CCl bonds. So 1 times CCl, which is 346. We have 1 C11C, which is equal to 612. And we finally have, I'm going to have to write in this very garish colour here, 1 HCl bond, which is equal to 432. So we add those up. So we do 3 times 413 added to 346 added to 612 and 432. And we get 2629. So it's not been a massive enthalpy change. 2629. Now, if we remember, from our equation that we wrote a little bit earlier, we do the sum of the reactants minus the sum of the products. So we're going to do 2691 minus 2629. If you're ever unsure about which way around to do it, this is the way around. This is how I think about it. This is the energy required to. What we're doing here is we're saying, what's the energy required to break all of the bonds in the products? So that is an endothermic process. So we can put a positive there. Then we say, what is the energy released when we form all of the bonds in the products? Sorry, in the reactants. All the bonds in the products. So that is an exothermic process. So that's always going to be a negative. So we can write those rounds that way around. And we do 2691 subtracted 2629. That gives us 62, which is a positive answer because we've already put the sign on. We know that whatever sign that comes out of this is going to be the sign for it. So we know it's an endothermic reaction, kilojoules per mole. And that is what I want you to do every time we do one of those questions, except you'll probably make fewer mistakes than I will because you're using a normal pen. Anyway, I hope that's been helpful. Please come prepared for Wednesday's lesson.